Hey everyone, in this video I want to dive into highly available network virtual appliances. We think about these virtual machines or virtual machine scale sets that are pre-configured with certain software to perform a certain network function, like a gateway, a firewall, part of an SD-WAN, whatever. So I want to dive into, well, how do we actually make these highly available in Azure? As always, if this is useful, a like, subscribe, comment and share really is appreciated, and please hit that bell icon to get notified of new content. Now, if I think about a network virtual appliance, it really is just some kind of virtual machine. And I could absolutely just have one of them. But if it's performing some kind of important function, that's probably not a good idea. There's going to be maintenance that needs to be performed, so it would be down for a period of time. There could be other instances where it would need to be down, maybe unplanned. Well, that's not a good thing. For scale reasons, I might want multiple of them. So we think about, hey, we need multiples of these NVAs. And we can't do some of the same things we do on premises around gratuitous ARP and moving IPs freely around. So what we'll often hear about is using those NVAs with a load balancer. And that's what I want to dive into this session. Often you'll hear about SNAT and, well, synchronous flows, symmetric flows, asymmetric routing. And I want to talk about what all those different things mean. So that's what we're going to do. But first, because we are going to talk about the load balancer, let's just go back and remember a couple of key things. Now, I have a deep dive video about the Azure load balancer, so that has all of the details, but I'm going to summarize really quickly. We can think about the load balancer is not like an on-premises load balancer. It is not a physical piece of equipment sitting on the wire between this thing and another thing. It's entirely in software. And it's really realized, made real, by we think about we have these muxes. So we have a whole ring of muxes that make up a certain instance of a load balancer. And that's multi-tenant. They handle all different load balancers for different tenants. Now, I can always think about, well, the load balancer has kind of a front-end IP. Now, load balancer can be internal or external. It cannot be both. Well, that front-end IP is basically made available on all of the muxes that are part of that particular ring. So through kind of Anycast, that wonderful thing, I can get to any of them through any of the muxes, which are all software components. So there's no single point of failure when we think about the load balancer. It is Anycast, so it's going to use equal cost multipathing to just go to one of them. So as a client, I could think about, hey, I'm sitting over here. I send a packet and the destination, I'm sending it to front-end IP1. Well, remember that front-end IP1 is surfaced by any of these muxes. So the packet goes to, let's say, that one. And then what we have is that's kind of the front end. Then what we have as part of the mux is kind of a back-end pool. So we have n number of possible targets it could send to. Now, in reality, let's just say we have a particular virtual machine over here. Well, that virtual machine actually sits on a physical box. That physical box has a virtual switch, and there's a virtual filtering platform that does various things. And so the key point, what actually happens is the mux itself does nothing. The mux does not change the packet in any way. It's not changing IP addresses, it's not changing it to this VM. All the mux really does is wrap it in GRE and forward it on to the provider address of that host. So that packet at this point gets forwarded on to the virtual switch through the virtual filtering platform. Now at this point, it does change the packet. It changes the destination to the IP address of that particular VM. So it now changes the destination to VM IP1 of that packet and sends it to it. Now, when this sends the response, obviously, well, it's going to have itself now as the source, which is not good. This is not expecting a response from this IP. So when the response comes back through the virtual filtering platform, it changes the source. Let's do the return in a different color. It now changes the source to the front end IP of the load balancer. And there's something we kind of call direct server return. And this always happens with the Azure load balancer. What is the point in sending the traffic back through the MUX? It doesn't add any value there. Let's save the utilization of the MUXes just to receive the traffic, which is normally a fairly small amount. Most of the kind of requests are fairly small. It's the responses that generally have all the data. So the response actually bypasses all of this and goes directly to the destination. So that's kind of a key point. Ordinarily, with a load balancer, the return traffic does not go back via the MUXes. It doesn't go through any hashing algorithm that the load balancer is doing. So all of these MUXes are doing kind of a hashing algorithm based on different things, 5 tuple, source IP, destination IP, source port, destination port, and protocol, to distribute that should be an even distribution on all the possible targets in that backend pool. But it doesn't need to send it back via them. It's just going to go direct. So that's kind of part of direct server return. So that's an important thing to realize, because when we start to think about NVAs, well, maybe I need the response to go back via some appliance in the middle. So that might be an issue. So we need to keep that in mind. Now there is a feature called floating IP. Now with floating IP, what this essentially does is this bit here where normally the destination gets replaced with whatever the backend set member's IP is, it doesn't do that anymore. So that gets taken out. So now it is just sent to the VM as going to FEIP1. Now when I do that, for the VM to accept it in Azure, I have to enable that VM for IP routing. So if I actually looked at the config, in this scenario, I would turn on kind of IP routing feature on the NIC, which would allow Azure to not check to say, well, look, is this packet actually destined for that VM or coming from that? It bypasses that. So if we actually went and looked at a network interface card, she would go to a virtual machine, for example. I would go and look at its networking. I would go and look at its NIC. And in the IP configuration, well, we have this IP forwarding option. So if I turn this IP, I think it's an IP routing. If I turn on IP forwarding, that's what it's actually called, that will then tell Azure, hey, don't bother checking if it really is this IP. It would just let it kind of go forward. And then what we would do, probably inside this guest OS, is add loopback adapters, for example, with that front-end IP. So I can have multiple of those to accept different IP addresses, reuse ports, etc. So it's kind of an important review that, hey, ordinarily traffic goes through the MUX, which is highly resilient. It's not a single point of failure, but it's not a physical thing. It's all in software. The response does not go back via the load balancer. If I don't want the IP to get replaced in here, remember it's translated on the way back, I can use floating IP. Now, another instance where it doesn't do this replacement is we're talking about the packet going to this destination, the front-end IP. But that may not be the case. I may be sending the packet to, let's just say, destination service IP1. But what I actually have is I have a user-defined route that actually says, hey, to get to the CIDR range, service IP1, you have a next hop of a virtual appliance, which is FEIP1. So it's saying, look, to get to this target IP address or CIDR range, which is a group of IPs, I'm going to override the default routing, and instead the next place you send this packet is you're going to a virtual appliance, and this is the IP of that virtual appliance, which happens to be a load balancer because we're going to make it highly available. In this instance as well, this IP replacement does not happen. So I'm sending it as the next hop, hey, to FEIP1, but the destination of the packet is SVIP1. So SVIP1 is what would get received into the VM. So it doesn't get replaced in that scenario. So understand those two scenarios when we think about, okay, using a load balancer, when it's a next hop, which is our scenario, the load balancer is not the destination. It's just a next hop in the routing. So there's going to be no IP replacement. So I have to have kind of that, I wrote IP routing. Again, we saw it was IP forwarding. So I'll actually just replace that to make sure I have the right word in there. So IP forwarding, because essentially it's forwarding on packets. It's routing, but it's forwarding on packets that aren't destined for itself. Then, hey, it doesn't replace that IP. There's one other consideration that I have to think about for the load balancer. And that is, in the physical world, we like multiple NICs. We like multiple NICs because a NIC gives us a certain amount of bandwidth. That physical NIC is connected to a certain piece of wire that goes to a certain switch that's on a certain VLAN. I can segment traffic. Well, in Azure, it really doesn't work that way. This is all software-defined networking. And so when I have a virtual machine, I have a NIC. Whatever I do, if I had 2 NICs, 3 NICs, 4 NICs, 5 NICs, the bandwidth available for the VM is the same. Adding NICs does nothing to increase the amount of bandwidth. We can go and look, for example, at the specification of certain virtual machines, and we'll see it talks about, hey, look, expected network bandwidth. It's a value. Yes, I can have a certain number of NICs, but that doesn't increase the bandwidth. If I have that 8 CPU VM, I get 4 gigabits per second. If I have 1 NIC or 4 NICs, in total I have 4 gigabits per second. So it does nothing to actually increase my amount of bandwidth. So my bandwidth is set, essentially. Additionally, this is layer 3. So it's flat. There is nothing I'm really gaining by adding additional NICs. Every NIC can get to everywhere on that VNet. I'm not gaining anything by adding additional NICs. If I want to control traffic, we use network security groups. Where we have the rules based on kind of CIDR ranges, or we can have application security groups, which let us in those NSGs use basically tags that we can put on the NICs. Or I'm doing routing. I'm saying, hey, go this particular next hop where I have some appliance that does checking. That's how we control the communications within a software-defined network. We're really used to having multiple NICs. It doesn't apply to the cloud. It's not getting you any actual benefit. So I do not need multiple NICs in most scenarios. And the big deal is it's going to break symmetric routing, which is something we often want with any kind of stateful appliance, where, hey, traffic is coming in and it goes to something, it does some work, and then I need to make sure the response to that traffic goes to the same backend member. And what we're going to see is that works when I have a single NIC. If I have multiple NICs, it breaks. There is no symmetric guarantee if I have multiple NICs. Each NIC is completely separate. The hashing algorithm works in a completely separate way. So this will break symmetric routing if I try and put multiple NICs on the virtual machine. And again, it doesn't really gain you anything. And the reason this is so important is when you start getting to your NVAs, I'm probably going to have more than one. I'm going to have n number of NVAs, and I want that symmetric routing. Again, if the packets came into this one and then went on its merry way, whatever that went to, when the response comes back, because remember, I'm going to have a load balancer that actually told this to go to that one. I need the response to go to the same one, because if it's stateful, it needs to see both the request and the response coming into that. So I need that stateful capability. So this statefulness, that's going to drive a lot of our behavior around our NVA configurations to make sure we have that. So a key point, and it can be tough, you have to get past the old way of thinking that, hey, I like multiple NICs to break up different things. It's just not something that's really done in the cloud. If you even look at some of the, and I'll talk about this, some of the reference architectures Microsoft has, even if it's like a DMZ and then internal networks, it's still one NIC. It doesn't need different NICs. It doesn't gain you anything. It's still a flat network it's connecting to. I segment and control using NSGs, ASGs, and various types of routing. Okay, so now let's actually talk about these different scenarios. Let's think about what I'm actually trying to do. So if I think about internal first. So by internal first, what I'm talking about is, look, I have some kind of maybe subnet here, subnet 1, and I have maybe another subnet over here, subnet 2. And it's important to remember, so these subnets probably have different, they're going to have different side ranges. Maybe this is 10.0.1/24, and this is 10.0.2.0/24. So they're two different side ranges, and I have things attached to them. Hey, look, there's a network interface card that links VM1 on that subnet, and then there's a VM over here on this other one. And then an internal pattern, what I actually want to happen is I want to go through some NVAs. Maybe they're firewall appliances. I want to go and check that traffic. Maybe NSGs are great and I use them for certain things, but I want to use maybe some firewall appliances. So what I have is I have a group of NVAs. And I have N number. It really doesn't matter. I'm just going to draw 3, but you could kind of go on. They each have one NIC. That's kind of an important point. There's just a single NIC in these things. And then remember, we're going to have an internal load balancer. Now it's going to be the SKU standard, because standard is going to let us do something called HA ports. And what HA ports does is ordinarily we have to define rules. We have to say, hey, it's for this port and this protocol, go here. With HA ports, we don't have to do that. It basically says balance all flows. So it's all TCP and all UDP ports. We don't need individual rules anymore. So we're actually going to do that. We're basically setting the front end, the back end ports to 0 and protocol to all. And this was actually created for NVAs. So we're going to have a standard internal load balancer. We're turning on HA ports. Now again, remember these NVAs, because they're going to be receiving traffic not destined for them, they're going to have that kind of IP forwarding configuration on all of those NICs to let them actually Azure send them the traffic that's not really for them. So the backend set is going to have all of these in it. And then this is going to have a front-end IP, which is an internal IP address. It's going to be on a subnet as well. So there we go. So it's going to be in a different subnet. We generally want to make sure we don't get some circular routing. It's in there as well. So that's the setup. So how does this work? Remember, we want symmetric routing. I need to make sure that when the traffic goes this way, the response goes back via the same NVA to let it actually pass through. So what we're actually going to do is, it's just going to work. There isn't a big problem. Now remember I mentioned that reference architecture. So this is an example reference architecture I did want to call out super quickly. Here you can see, hey look, we have like a DMZ subnet here. Then we have these different VNets over here. Notice the NVA, like I said, it sits in its own subnet with the load balancer using an IP from there. But it's just one load balancer. It's one NIC on all of these NVAs. I don't need multiple NICs. I can control things through NSGs, but also all these NVAs, if it's a firewall, it's just going to be controlling that anyway. So I don't really have those big challenges with, well, how am I going to handle that? Okay, so let's think about what's going to happen here. I want to talk from VM1 to VM2. Now, ordinarily, Azure, just in the VNet, will have routing that's going to let that happen. But remember, I want to redirect them through to these NVAs. So the way we do that is user-defined routes. So I can create a user-defined route. And what a user-defined route is, I'm modifying the routing. I'm doing some custom routing. And I'm going to say, look, to get to this subnet, so that's a CIDR range. So to get to 10.0.2/24, you define a next hop. This is where you go next. And because it's a flat network, because it's software-defined networking, it doesn't have to be something in the same subnet, so it's fine. I can go and send to this front-end IP that's in a different subnet on the VNet. So my next hop is going to be of type virtual appliance, and I'm going to give the IP address of that front-end load balancer. Because remember, what the load balancer is doing, it's going to distribute evenly between the back ends, and it's also doing health probing. It's checking, are you available? And if one went down, well, it would find out it's not available and stop sending traffic to it. So what the load balancer is doing is giving us the distribution and making sure we only send traffic to healthy ones. So now I said, okay, great. So when this VM wants to send to this one, it knows, oh, okay, yeah, I have to send it this way. So my packet essentially is going to go that way. At this point, the load balancer does that rendezvous hash algorithm. And what you can really think about happens is it looks at that destination and source IP address. Again, there's other things, but destination and source. And then it's got buckets it can land in, like a modulus. So I can think about bucket 1, bucket 2, bucket 3. And it's going to, by nature of the hashing, it's going to evenly distribute the traffic. So let's just say in this example, the rendezvous hash for that source and that destination is going to land in the first bucket, and it goes to that NVA where it's doing some checking. Now remember what happened. So it's doing its checking, it's saying, okay, that's valid, that's allowed to happen. Then it's going to forward it on. But remember, the forwarding doesn't go back via the load balancer. It basically goes to the host and goes to the virtual machine. That's the pattern. Well, I need to make sure the response, because remember, ordinarily it wouldn't go to the load balancer. It does that whole direct server return part of the flow. It would now just go direct, which I don't want. This is stateful. I want it to see the response and check the response. So now we have another UDR on this subnet that says, hey, if you want to get to 10.0.1.0/24, then your next hop is a virtual appliance, and it's that same front-end IP1. Again, remember, because it's a next hop, there's no IP modification in the virtual filtering platform of the box, because it's not the target. This is seeing the NVA right now is seeing this VM as the source and this VM as the destination. It's doing checks and then forwarding it on because we have that IP forwarding feature turned on. So now the response, okay, response. Now the nature of the rendezvous hash, this uses, even if we switch the source and destination, because remember in this way, the source was VM1, the destination was VM2. The response, the source is VM2, the destination is VM1. The source and destination have switched, but it doesn't matter. The rendezvous hash, the way it works, it will still end up with the same modulus, the same bucket. So even though the source and destination have switched, this is going to go to this NVA. It will do whatever checks, and then it will forward it directly, and there's the response. So that's how it works. So I can think about, hey, there was some request, and then there was some response. And by nature of the way the rendezvous hash works, it's going to go to the same backend member. It just works. So the key thing is there is no NAT. There is no network address translation required. I don't have to, I could if I wanted to, but I don't need to. I don't have to replace in the NVA the source, instead of being VM1, it being the NVA's IP address. I don't have to do that. So that was actually fairly easy. And again, remember, if a particular NVA went down, the health probing that load balancer was doing would see it was down, and then it would rebalance the traffic. Obviously, there'd be a certain state break there because, hey, it didn't see the outbound, but appliances would generally handle that in some way. And it shouldn't really happen. The nature of how fast these things go, hopefully you won't see that as a big problem. But just be aware that that could happen. So this was very pleasant. This is very pleasant. Oh, this was nice. This just kind of works because it's internal. And the whole reason it works is I can set an internal load balancer as the next hop. That was kind of the key thing that made this all possible. Next hop could be an internal load balancer. All right. So that was the nice, pleasant scenario. Now let's talk about another scenario. So now let's think about, well, an NVA is sandwiched between an external and an internal load balancer, because I want to make something available publicly. So now I can really think about for a second, okay, let's just say we have two NVAs. We're going to simplify this a little bit. So I have an NVA 1 and an NVA 2. Remember, a load balancer is internal or external. It cannot be both. So now I have an external load balancer, and it goes here. Now, it is fairly common at this point, people will use multiple NICs. Again, you don't have to. If you look at Azure Firewall, it actually has a NIC, but it connects to two load balancers, an external and an internal. I don't have to have multiple NICs, but it may do. It doesn't really influence things at this point because it's different load balancers. So the hashing is going to turn out differently anyway. So I could think about, hey, maybe there's a NIC on this side or not. Again, it could be one NIC that they connect to. And then I have an internal load balancer. So I have this pattern. And I can think what's really happening at this point is that there's some source out here on external network that is sending. And remember, there's an IP address. So it's sending it to this IP address. So it's sending it, hey, to this ext IP1, whatever that is. Remember, the internal, it still has its kind of front end IP1. And then there's some targets down here at the bottom. Again, there's a VNet, there's maybe a VM or multiple VMs, whatever that is, and it has a certain IP range. Maybe that's the target. We have a problem here, and you might start to see it already. So a packet comes in here. It's going to go through a hashing algorithm. Let's say it picks this backend pool member, and then it does whatever work it's going to do, and it sends it here. Great. Now it sends the response. So it has to have, again, a UDR. Now that UDR could be specific to some external IP space, or it could kind of be a default route. It might be kind of a 0, 0, 0, 0, 0. My next hop is a virtual appliance, and it's FEIP1. So my response is going to go here, where it does a hash that is completely different. There's no relationship between these anymore. By luck, it may go to this bucket, but there's no guarantee of that at all. So at this point, I'm stuck. And honestly, so with this internal one, sometimes people will create maybe a second NIC on an internal because they're old school and have a NIC for DMZ, a NIC for internal, they have different front-end IP addresses. And it's that same, there's no guarantee. Even if it's the same load balancer, if it's different NICs, the hashing will break. You may get lucky. It may happen that it lands on the same bucket, but it may not. There's no guarantee of that. The only way to guarantee symmetric routing is single NIC. That's the only way this will work. So I'm here. What do? Well, it comes down to, can I SNAT? SNAT is source network address translation. I am allowed to change the source of the packet. Now, if the answer is no, we're in this world. Now, sometimes people don't like SNAT because then the back-end resources, they see the source as NVA1. And I don't want that. I don't like that. Now, remember, it's not really the end of the world. And I'll talk about the solution to that in a second. But let's say it's unacceptable. I cannot change the source IP address. Well, essentially at this point, I can't run active-active. I just can't. I have to run an active-passive motion. I.e., this one is essentially not running, not accepting traffic. And so then what happens is the health probe of this load balancer only sees this one as alive. Likewise, the health probe of this load balancer only sees this one alive. So it's only can send to one of the load balancers. So the response, well, it only has one choice. It has to go this way. And then sure, it will go and send it. It will go and send it to the originator. So if I cannot do SNAT, I can't run active-active. Because there's no way to guarantee it goes back to the same NVA it was received on. Because these are completely independent hashing algorithms, there's no guarantee they're going to land on the same one. So I can't do it. So I have to have a UDR to tell it to go to an internal load balancer, and I can only run one active. So if I think about scaling, hey, I need to accept more traffic, I just have to scale up. I make it bigger. That's the only thing I can do. Okay, well, it's not ideal. We're not super fans of that, but at least we get symmetric routing. Because remember, if we did active-active, well, the response might go that way, and it's now asymmetric routing. If it's stateful, it will break. So what if we can? What if we can SNAT? So we get the same scenario again. Let's see, I'll redraw the picture. So we have the same external. I'll draw a bit quicker. We have the same, I'll draw two, but things do kind of change here. We have the same internal. Oh, drawing that wrong, so I'm rushing. Oh, I should have just copied that. So now we have an internal load balancer. Again, remember this has external IP1. This has some front-end IP1. Again, you can have one or two NICs. It doesn't actually change anything because it's a flat layer 3 anyway. And then I have kind of that target. So we have all of these various things. It looks exactly the same scenario. But now I'm allowed to SNAT. So what does that mean? So SNAT means I'm allowed to change that source IP. So now as the request comes in, again, we go through the hashing algorithm, and you may be wondering, look, why in the UDR, why point to this load balancer? Surely if I point it to this load balancer, I fix the problem. Same load balancer, same hash, it works. You can't have a next hop of an external load balancer. Not allowed to do it, doesn't work. So that's why we have to point to a different load balancer. So now this happens, okay, the packet, it picks one, and it ends up on this one. It's now allowed to change the source IP. So the source IP was this, whatever that was. It's now going to change the source to be NVA1. Okay, that's good. Well, now what happens? It can change it. So now what it's going to do, the packet, carries on kind of its merry way, when it sends the response, who is it going to send the response to? Well, it thinks it came from NVA1. It then does the reverse. It now replaces the destination to, instead of being from NVA1, it will swap the things out to make it look like, hey, now it's external IP1, and sends it back. So if I can do snatting, it's a very different world. My scale, I can now scale outwards, and it just works. Because I can replace who the packet came from, well, so this will just send it. I don't even need a UDR. There's no UDR needed. Now, I might still have a UDR as a default for certain things, because I still want to check through. It depends on the type of appliance. So I still might have a UDR to go into other things, but the target, the destination it's sending to, is this particular NVA. It's going to land up on that NVA. So that's kind of the key point. If I can SNAT, I can handle this. Now what if this one needs to see the source IP address? So remember, there is a function called X forwarded 4. It can be added to the IP header, and it could actually add in, hey, IP1. So now whatever is running inside this VM, yes, the source says NVA1, but if they go and look at the headers, it will say, hey, X44 actually was IP1. So they can still actually go and see who was this for. And the whole point is these are now active for however many I have. I can now have that scale motion, and I'm good. It's going to work. So if I can SNAT, it changes things enormously, because I can ensure symmetric routing, because I'm going to replace who it came from. So I know it's going to come back to the same NVA. Now there is, remember I mentioned floating IP? I can use that on both of these. So both scenarios, I can optionally turn on floating IP. And remember, all floating IP does is, hey, I'm not going to, when this packet comes through here, if this, because this now is probably the target. This is not a next hop scenario coming in. This is actually the target. The target this packet's going to is external IP1. So when it hits the NVA, it will have the NVA1's VM IP address as the destination for both of these. Because remember, this is not a next hop. This is coming in. This is the destination the packet's being sent to. Well, maybe I want to be able to have multiple IPs and then reuse the same ports that this is listening on, and actually let the NVA decide, well, it was going to this IP address, so I do something different. So if I turn on floating IP, I actually see the well, in this case, it's the external particular IP in the NVA. So I could turn that on for either one of these, and all that would now let me do is I could have external IP 1, 2, 3, 4, 5, all on this external load balancer. And then remember, in the NVAs, I would create like loopback adapters for each of those IPs. So Azure doesn't really know they exist in this VM. It's just kind of internal to the OS, the NVA. But now it could do different things, route them differently based on what IP it was actually sent to on that external load balancer. So that floating IP can be useful in that scenario. So that's really the summary. If I'm internal, it's easy. It's just going to work because make sure you have a single NIC. I'm going to get symmetric routing. I don't need NAT. If it's external and it's sandwiched, well, now I have to have two load balancers. So I can't just get the symmetric routing automatically. So either I had to have an active-passive motion if I cannot SNAT, or if I can SNAT, well, then I can go back to active-active. I don't want to go into detail, but there is another scenario. And the other scenario is when we have route server. Now I'm going to do a video on route server next week. So I don't want to go into a lot of detail, but in a week there'll be a link up there for route server. Remember, the whole reason we have the load balancer is because the NVAs ordinarily can't share an IP address. They can't move the IP address between them easily. And if one of them is down or there's a problem, there's no way to adjust the routing to say, hey, don't send to me. Well, if you think about things like ExpressRoute and site-to-site VPN, they handle that. And the way they handle that is essentially the virtual network it exists on has a routing table. That's what UDRs do. We modify the routing table. And it updates all of these things using something called BGP, Borderless Gateway Protocol. Well, I can now have NVAs. Now those NVAs talk to something. Maybe they're gateways, SD-WANs, there's a certain IP range up here that they represent. Maybe they're a default firewall for everything, so it's a 0000/0. If I add in Azure Route Server, I establish a BGP peering from those NVAs to Azure Route Server. This is not sending data to Azure Route Server. This is just exchanging BGP. So it's telling it, hey, I'm talking to this CIDR range. This CIDR range up here. Azure Route Server then updates the routing table. So it updates the routing table to say, hey, if this is CIDR 1, hey, to get to CIDR 1, use NVA 1. And because there's two of them, hey, to get to CIDR 2, use NVA 1. Well, at this point, it would use equal cost multipathing. So now the services in this VNet or connected to this VNet, again, it's BGP, it's going to exchange routes with peers, etc. Now if I'm using this, technically I don't need the load balancer. I'm going to look at the routing table, and again, equal cost multipathing, I'll send to one of them to actually send the various traffic out. Now, the load balancer is super nice because remember that health probe, it's very fast. If there's an incident with one of these, it's going to detect that super quick, update, and stop sending traffic there. Today, the convergence on the BGP, it could be, I think it's like 3 minutes. That's a lot slower than the load balancer. So in terms of actual convergence, the load balancer is a better scenario here. Where we are starting to see this is SD-WAN scenarios. So in SD-WAN scenarios, that's the main use case here today. They're starting to use Azure Route Server. Because again, think about the complexity. If I'm an SD-WAN, well, these IP ranges change fairly frequently. So user-defined routes, doing that stuff manually, can actually be pretty painful. So now, because I'm using BGP to Azure Route Server, it updates the route server dynamically what it learns from BGP. Hey, I solve a part of that problem as well. Again, I'm going to talk about route server in a lot more detail next week, so I'll have a link up there. But I just wanted to call that out because there is starting to see some alternatives, especially around kind of the gateway type appliances. Maybe now we can start to use Azure Route Server, but don't ignore the fact that, hey, the load balancer still actually adds a lot of value. So even in this motion, longer term, we still might put load balancers here to give us some additional convergence capabilities, and the BGP will be updated with kind of the load balancer, but it will still let us now learn the routes dynamically. So kind of the summary of that is the load balancer is probably still preferred for most scenarios today. But there might be some options depending on exactly what you're doing. But that was it. So that was thinking about all of the different kind of considerations for highly available NVAs. I hope that was useful. I hope it made sense. Again, I've got that deep dive on load balancer. Look at that, understand it. The point is it's not a physical box. It's not a single point of failure. Realize in a layer 3 flat network, having multiple NICs really doesn't do anything anyway. So you have to try and get past the on-premises bits of wire mentality. Doesn't apply. We separate with NSGs, ASGs, routing. Symmetric routing is super important. And as soon as we have multiple load balancers or even multiple NICs, it's going to be different modulars, different hashings going on. It will not land on the same one. Internal, easy. External, where I have 2 load balancers. Depends on whether I can have NAT or not. and then potentially route server in the future. So again, I hope that was useful. Again, please subscribe. Your support is appreciated. Until next time, take care.